Hey everyone, this is Juan Ramirez with chapter 15.4, the inverse Laplace transform for EE 2715, linear circuits to transients. So previously we looked at how we could convert a signal that's represented in the time domain, how we could convert that into something called the S domain or the Laplace domain using the Laplace transform. We looked at the different properties of the Laplace transform as well as Laplace transform pairs that we use to make those transitions into the S domain a little bit easier. Now we're going to look at how to take a function that's represented in the S domain or Laplace domain as a time domain signal. Alright, so to convert a signal from the S domain to the time domain, we use the inverse Laplace transform. At a high level, that encompasses two steps. First step is to simplify the function or decompose it. And we'll decompose it a lot of times using partial fraction expansion or partial fraction decomposition. And then the second step is to, use pairs and properties of the Laplace transform to find the inverse Laplace transform. Alright, so first we'll cover a brief review of partial fraction decomposition. And then once we cover that refresher, then we'll apply it to taking the inverse Laplace transform and do a few examples. Okay, so consider a function that is represented as a quotient or a fraction with a numerator and denominator. So let's say let some function f of x be equal to p of x over q of x, where p of x is the numerator, q of x is the denominator. Both p of x and q of x are polynomials. And another important aspect of this type of decomposition is that the degree of p of x must be lower than the degree of q of x. By degree, we mean the highest degree of the polynomial. So for example, if the polynomial is x squared plus 3x plus 5, the degree would be 2. So the degree of the numerator of p of x has to be smaller than the degree of q of x. That means that it's in fact, well, the degree, or rather, let's say, if you were to do long division, your answer would simply be a fraction. Otherwise, if the degree of p of x and the degree of q of x were equal, or if the degree of p of x was greater than the degree of q of x, when you did long division, you'd end up with an answer and a remainder. Okay, so what are the steps for partial fraction decomposition? First, we're going to try to factor the denominator as much as possible. Next, we will, for each factor of q of x, determine the term required for partial fraction decomposition based on a table that I'm about to show you. Okay, so once we've determined that term for each factor, we're going to set up the equation. And lastly, we will solve for constants. All right. So first of all, let's look at that table. What's that table actually look like? So we're going to say there are 3 cases. And each case is for a different type of factor of q of x, the denominator. And next we're going to look at the term in the partial fraction decomposition. So if the factor comes out to ax plus b, which is the simplest, the associated term that you would write is constant a divided by that same ax plus b. If you have ax plus b raised to some power k, then the term associated with that factor of q of x would be a1 over ax plus b. Sorry, it's a little tight. Plus a2 over ax plus b squared plus up until ak of ax plus b to the k power. And that's for integer values of k. So if the term, or if the factor of q of x is ax plus b to the 3rd power, the associated term that you'd set that equal to in that equation would be a1 over ax plus b plus a2 over ax plus b squared plus a3 over ax plus b to the third power. Okay, let's look at the third case, which is ax squared plus bx plus c. When you have a factor like that, the associated term is ax plus b all over ax squared plus bx plus c. Now, you should differentiate the capital A and the lowercase a, and the capital B and lowercase b, those are different. The lowercase values you're getting from that actual factor, those will be known. The capital AX, or capital A, capital B, are constants that we're going to solve for. Okay, so this is the table we're going to use. Let's start by doing a few examples. All right, example 1. Let's say we want to decompose x squared plus 4 divided by 3x cubed plus 4x squared minus 4x. Okay, so if we remember the steps, the first step is to factor this fraction as much as we can. I mean, before we can do that, we have to know that the degree of the numerator is smaller than the degree of the denominator. And the degree of the numerator is 2, because the highest degree of x is 2. The degree of the denominator is 3. 2 is smaller than 3, therefore the degree of the numerator is smaller than the degree of the denominator. We are able to do partial fraction decomposition. Okay, now we will rewrite this such that the denominator is fully factored. I see that all terms in the denominator have an x, so I could factor that out. And then I'm left with 3x squared plus 4x minus 4. So I think I could do 3x x. I can do 3x minus 2 and x plus 2. Good old algebra days. So now I am going to try to set up an equation where for each term I create a term in the partial fraction on the right hand side. Okay, so the first term in the denominator is x. What does that most look like out of the 3 cases? It looks like case 1, where the value of a is 1, so 1 times x is x, and the value of b is 0 because it's not adding by anything, it's just x. Okay, so this term will be equal to capital A all over that ax plus b, which is just x. Alright, now let's look at the second factor in the denominator. That's 3x minus 2. Again, that looks like the case 1, ax plus b. You can say plus. And here, ax plus b is equal to 3x minus 2. In the denominator, the numerator will just get a constant, and I'll call it capital B so that I can distinguish it from capital A. Finally, the last one is x plus 2. Again, that's a form of case 1, ax plus b. The denominator will keep the same values. The numerator of that term will be c. Now, I will try to solve for capital A, B, and C. So once we've set these partial fractions equal to the sum of the terms associated with each factor, we're going to create a common denominator. Alright, so how do I do that? If we recall, we'll multiply, so the a over x term, I'll multiply by 3x minus 2 times x plus 2 on both sides. Right, so essentially I'm multiplying by 1 because I'm multiplying denominator and numerator by that same thing. But I do that so that now this term has the same denominator as the one on the left-hand side of the equation. I'm going to do the same for the second term. So I have to multiply it by x and x plus 2. And finally, I'll do the same over here. Have to multiply by x and 3x minus 2 so that the denominator is the same. Alright, well now what we have is a case where the denominators are all the same on the left and right hand side of the equation. That means that the numerators have to be the same because otherwise it wouldn't be equal. So from here I can say I know x plus 4 is equal to a times 3x minus 2 times x plus 2 plus b x times x plus 2 plus c x times 3x minus 2. Alright, now we go into that one step we spoke about where we solve for those constants. So what I'm going to do is I'm going to plug in values of x that will eliminate 2 of the 3 terms. First value I notice is that on the second term, bx times x plus 2, and the third term, cx times 3x minus 2. If I plug in a value of 0 for x, those whole terms will go to 0. And it'll leave me with a equal to something. Okay, so let's do that. X is equal to 0, what's going to happen? Three times 0 minus 2 is negative 2. 0 plus 2 is 2. B times 0 times 2. C times 0 times negative 2. The second and third term go to 0 because you're multiplying by 0. So you're left with 4 equal to negative 4a. Therefore, a is equal to negative 1. Alright. Now I know what a is. Still want to know what b and c are. Okay. Turns out what we end up doing is we end up substituting the zeros of that denominator. So if we look back up here, maybe I'll do it in a different color. The 0 of the first term in the denominator, x, was x equal to 0. The 0 of the second term is 3x minus 2 equal to 0, so x is equal to 2/3. And the third 0 is x plus 2 equal to 0, so x is equal to negative 2. So those are the values of x that I'm going to substitute. Alright, so I just did x equal to 0. Now let's do x equal to negative 2. And that'll give us negative 2 squared plus 4 is equal to, the a term goes to 0, the b term goes to 0, and then c multiplies by negative 2 times 3 times negative 2 minus 2, which is negative 8. Okay. So what do we end up with? We end up with 8 equal to 16 C. Therefore, C is equal to 0.5. Okay, and finally I'll plug in x equal to 2/3. The a term goes to 0. The b term goes to 0. Oh, no, the b term does not go to 0. B term multiplies by 2/3 and then by 2/3 plus 2. The c term goes to 0 because of the 3x minus 2. When you plug in 2/3, that'll go to 0. Okay, you do some math with a calculator in this case, and you end up with 4.44 equal to 1.78 b. B is equal to 2.5. And then we look at our inequality, our original one, which was x squared plus 4 is equal, or sorry, divided by x times 3x minus 2 times x plus 2. That's equal to all those three terms that had the a, b, and c. Now I'll just rewrite those. So you end up with, what was a? A was -1, so -1 over x. What was b? 2.5, so plus 2.5 3x minus 2. And then what was c? 0.5, so plus 0.5 x plus 2. All right. So we just decomposed that partial fraction. Now let's do examples where we actually also do the inverse Laplace transform. And along the way we'll see other cases, so case 2 and case 3. So example 2. Find inverse Laplace transform of some S domain function The S domain function in this case was already factored for us, right? The denominator we can't factor more, but we could tell that the degree of the numerator is 1, because you have an S, so S to the first power. The degree of the denominator is 2, because you have 2 S's. So if you were to actually expand that denominator, it would be S squared plus 2S. So this is okay to do partial fraction decomposition. So for the first term, which is S, again, we're going to have A over that term, because it's that first case of the table we spoke about. The second term is also the first case of that table. S plus 2, and the numerator will be B. And now we're going to solve for A and B. Before doing that, we want to find a common denominator. So we set those equal to A times S plus 2 all over S times S plus 2 plus B times S all over S times S plus 2. Now they have the same denominator. The left side is equal to the denominators of the right side. So the numerators must be equal. All right, and then we'll substitute values of S that are equal to those zeros of the original function. We want to go here on the right. The zeros are S equal to 0, and then S plus 2 equal to 0, so S equal to -2. Plug in S equal to 0, you end up with 0 plus 4 equal to A times 2 plus B times 0. Therefore, a is equal to 2. Now we'll do s is equal to negative 2. Plug that in, we end up with negative 2 plus 4 is equal to a times negative 2 plus 2, which is 0, plus b times negative 2. That'll give us 2 equal to negative 2b. Therefore, b is equal to negative 1. So now we have decomposed this fraction such that we know the S-domain function can be rewritten as a, which is 2 over s, plus b, which is negative 1, so instead of the plus, we just put a minus 1, over s plus 2. Now we want to actually take the inverse Laplace transform to find the time domain function. To do that, we're going to take the inverse Laplace transform of each term. Okay, and that's when we looked at the table, and in the Laplace transform pairs table, we see that an S-domain 1 over s is transformed, if doing the inverse Laplace transform, to a time domain function u of t. But then there's a numerator of 2, or a coefficient of 2. So it's going to be 2 u of t for the first one. The second one has the form 1 over s plus a, which will give us e to the negative at. So it'll be e to the negative 2t. But we have a minus there, so that minus carries as well. And that will be our inverse Laplace transform. Right, example 2, not too bad. We'll do a few more examples. Example 3. We're going to say find inverse Laplace transform of f of s equal to e to the negative 4s times s plus 1. Okay, here we can't just right off the bat do partial fraction decomposition. The problem with doing that is the numerator is not a polynomial. So if you remember, that was one of the requirements. But I could rewrite the function as e to the negative 4s times 1 over s plus 1. And then if I look at our Laplace transforms properties table, you'll see that you can multiply an e to the negative as times some Laplace domain function, f of s. That'll be what we call a time shift. So for a time shift in the time domain, you multiply the Laplace transform of the regular function in the time domain times e to the negative as, where a is the actual time shift. So take a look at the time shift property on that table. But for now, I'm going to just write that this part of the function we treat with the time shift property. And what I really want to find the Laplace transform, or rather inverse Laplace transform of, is the 1 over s plus 1, which we don't have to decompose because it's already in the sort of decomposed form. We could tell that the associated time domain function for 1 over s plus 1 will be e to the negative t. Because we'll use the 1 over s plus a general form, the value of a is 1. The time domain function for that is e to the negative at. So there we have it. So our time domain function for the whole thing will be e to the negative t, but with a time shift of 4. So instead of t, I'm going to say t minus 4. And then you have to multiply by a step function that's time shifted by 4. So take a close look at the Laplace transform properties table. This is kind of a simple example using that, but if you're still sort of, putting your head around that one, take a closer look at that. Okay, now let's do two more examples. In example 4. We are going to do the inverse Laplace transform of some s domain function g equal to 8 over s times s plus 1 squared. So already this is sort of a simplified denominator, kind of ready for partial fraction decomposition, but we still do have to actually do the decomposition. The first factor is s, so the associated term will be a over s. That's a pretty easy one. But the second factor is s plus 1 squared, so now it follows the case 2 of that table we wrote up earlier. The way that will look is b1 over s plus 1, b2 over s plus 1 squared. And then we'll try to find a common denominator. So the common denominator will be s times s plus 1 squared. So we'll have to multiply the first term by s plus 1 squared, numerator and denominator. Second term by s and one more s plus 1. The denominator had 1 s plus 1. Just multiply one more to get it squared. And then the third term you just multiply by s. Okay. So for this one, the two zeros are s equal to 0 and s equal to -1. But two zeros alone won't find the three coefficients. We're looking for a, b1, and b2. So what you'll do is you'll plug in s equal to 0. And when you do that, you're going to find a equal to 8. I'll let you guys do the algebra behind it. If you plug in s equal to -1, you'll find the value for b2. And you'll find that b2 is equal to -8. What you do then is you're out of your zero, so what are you going to do? You're going to rewrite that equation with a and b2 already substituted in. So I'm going to say then 8 is equal to 8, which is the value of a, times s plus 1 squared, plus b1, we haven't found that yet, times s plus 1, plus not plus b2, rather minus 8, which was the value of b2, times s. The only thing we're looking for now is b1. So literally just plug in any value of s except for 0 or -1, and then solve for b2. So I'm just going to say s equal to 2, and that'll be 8 equal to 8 times 2 plus 1 squared plus b1, 2 plus 1 minus 8 times 2. You do some math and you should end up with b1 equal to -8. Therefore, g of s can be rewritten as 8 over s minus 8 over s plus 1 minus 8 over s plus 1 squared. And if we look at our Laplace transforms table, the inverse Laplace transform for each one will be 8 times u of t minus 8 times e to the negative t, right? 1 over s plus a. The time domain transformation of that would be e to the negative at. And then finally, the third one is a slightly different one that we haven't done in these examples. Again, you're going to keep your minus 8. When you have an s-domain function in the form 1 over s plus a squared, you'll end up with t times e to the negative at. So t, e to the negative, and then a is 1, so negative t, like that. Alright, you should be doing all these examples with the Laplace transform table, the pairs table, and the properties table, either printed out or opened in your textbook right next to you. The page of your textbook for those tables, if you're using the 6th edition of the Fundamentals of Electric Circuits book, it's page 685, table 15.1 and 15.2. That'll kind of simplify a lot of the work we're doing, or you can kind of see why I'm able to do these without spending too much time. All right, we'll do one more example. Our last example is example 5. We're going to find the inverse Laplace transform of some s-domain function x, which is equal to 4 minus e to the negative s all over s squared plus 5s plus 4. Okay, again, the numerator is not a polynomial, but the numerator is also not just an e to the negative at like we had for our previous example, example 3. It's a 4 minus e to the negative s. What we want to do for this one is you want to actually split those up. So the numerators you get split up because the denominator is the same. And if you do that, I'll kind of write it out. It would be, you can factor out the s squared plus 5s plus 4. And once you factor it out, you can kind of multiply each numerator by the denominator. By numerator, I mean 4 and e to the negative s. Okay, so now you have two different partial fractions. With each of the partial fractions, we'll decompose them separately. All right, so the first one we'll decompose is the 4 over s squared plus 5s plus 4. If we recall, the first step to decomposing is to simplify that denominator, which we can do, right? It's equal to 4 over s plus 1 times s plus 4. So then you set that equal to a over s plus 1 plus b over s plus 4, because it's that first case of the table we covered earlier for how to decompose certain types of factors. All right, then we find a common denominator, and once you do that, you end up with 4 equal to a times s plus 4 plus b times s plus 1. You plug in the different factors, so one of the factors is s equal to negative 1. When you plug that in, you should end up with a equal to 1.33, which is equal to 4 over 3. When you plug in the other 0, which is negative 4, you should end up with b equal to negative 1.33, or negative 4 over 3. Okay, well then, there's the other partial fraction. After sort of, for a second, disregarding the fact that there's an e to the negative s, we probably remember from example 3 that all that will do is add a time shift. So disregard that for a second and only look at the 1 over s squared plus 5s plus 4. We do have to decompose that separately because the numerator 1 is different than the numerator 4. So you end up with 1 over, and then we simplify that denominator again to two terms, or two factors, s plus 1 times s plus 4. And then I'm going to call these c over s plus 1 plus d over s plus 4. And finally, create a common denominator, at which point the numerators are equal. You end up with 1 equal to c times s plus 4 plus d times s plus 1. You should end up, if you plug in those same zeros, you should end up with a value of c equal to 0.33, or 1/3. When you plug in negative 4, you should end up with d equal to negative 0.33, or negative 1/3. And now you have values of a, b, c, and d. So what I'm going to do is I'm going to rewrite that s domain function with the decomposed fractions. So that was your value of a, value of b. Let's not forget the time shift, e to the negative s, but then that's multiplying by value of c and the value of d. And when we do that, you could then do the inverse Laplace transform using the tables for each individual term. So that'll be 1.33 e to the negative t, because the value of a in the 1 over s plus a form, the value of a is 1, minus 1.33 e to the negative 4t minus, and now that e to the negative s is just going to add a t minus 1, or a 1 value time shift. That'll give us 0.33 e to the negative, but instead of negative t, which is what it would be normally, you have this time shift of t minus 1. Minus 0.33 e to the negative time shift of t minus 1, but actually you have a value of 4. So it would normally be e to the negative 4t, but it'll actually be e to the negative 4 times t minus 1 because of the time shift. And then you have to multiply those by u of t minus 1. So let's kind of rewrite that for simplicity. You can factor out the 1.33 value. And then we can factor out the 0.33 u of t minus 1. And that is the time domain signal associated with that S domain signal. Once we applied that inverse Laplace transform, again, this one was a tricky one because the numerator, it wasn't a polynomial, but it also wasn't exactly just a time shift. You had to split that up first into the part of the function that had the time shift and the part that didn't, and then decompose both of those fractions separately. Once you did that, then you could actually do the inverse Laplace transform for each term. Alright, as always, please take a look at the examples in the book to get some more practice and become more familiar with the Laplace transform properties table and the Laplace transform pairs table. Definitely suggest you print one of those, or print both of those out and use those as you work on your homeworks and these examples. Thank you.